I did it, cool.
All right. We're gonna do some net ionic stuff today. Um, we study net ionics in honors. The thing about net ionic equations, the breakdown of all the little teeny tiny things that happen during a reaction, is that your solubility rules are a really big part of it, which are S's and AQs. So we're going to be marrying together some stuff from last year and then throwing in stuff from lecture one, which was strength of acids and bases. All of those things connect today. So maybe you did some work over the weekend and you're feeling all right about things. But the very first thing that we have to do is remind ourselves of what these two items mean. What does AQ stand for? Ooh, aqueous. Very good. All right, and then what does aqueous actually tell us about a compound? That it is soluble. All right, well, I'm glad that we're going over this then. Um, what does S actually stand for? Solid, yes. All right, the S stands for solid, meaning it's a precipitate, is the nice word for that. And it stays solid because it's insoluble. So the AQ and the S were items that we would labels that we would apply to parts of a reaction, reactants yielding products. And it would just tell us right away that if you labeled it AQ, it means that at that point in the reaction, it was dissolved. It was dissociated, which connects back to what we talked about on Friday. But if it had the S label, then it was staying solid. You could just see it sitting at the bottom because it was not dissociating, which again, we discussed recently. So, with that said, we've got the solubility rules. In honors, we don't make you memorize it. In AP, they're not going to give it to you, so I can't give it to you. So one of your big missions, for Unit 2 is to learn your solubility rules. Now, the good news is that, in my opinion, your exposure and repetitiveness with them gets them in your brain to the point where you might not have to sit down and actually make flashcards or anything. Because really, the ones that show up the most are your halogens, your nitrates, and then your ammonias. But let me remind you how these rules work. Whenever you're trying to label something as S or AQ, all right, is it soluble or insoluble? You have to look at the components of the compound. The bold rules, rule 1 and 3, and what I'm saying is what the italics say, but the two bold rules are the ones that overpower the other three. Sometimes there's compounds that contradict each other, where one of these 5 rules will say it's soluble, while another one of the 5 rules will say it's insoluble, which sounds really annoying, but every time that happens, one of the rules will be one of the bold rules. What do I call the bold rules? Do you remember? Those are the Big Daddy rules. And if Big Daddy says it's so, then it is so. All right? So, the point being that if something ever contains an alkali metal, ammonia or nitrate or my chlorate or my perchlorate, if they're in a compound, it's always soluble, no matter what the other rules say. So the Big Daddy rules are the most important ones. But then we've got splashes of the others. Now, I do want to point out that there are exceptions living in some of the others, meaning that these halogens are usually AQ because it says it's usually soluble, unless they're bonded to certain things. So, with that in front of us, we will do a little bit of practice. By the way, I do have these memorization things that I used in college. There's a lot of them that float around out there. So if you're wanting to look for ways to remember different things, then do that. But I do want to tell you that in the AP, in the room in May, nothing makes me happier than the proctor telling me, I heard one of your students whispering Sri Lanka to themselves. It was really weird. That makes me a proud teacher when y'all do that. But anyway, you don't have to use mine. Come up with your own, whatever. I don't care. but you do have to know them. So let's practice a little bit. Silver nitrate is our first example there. So we're dealing with silver nitrate. All right, so make sure we're able to do the nomenclature. And all I want to know, is it S or AQ? Is it soluble or insoluble? Which rule do you see jump out at you immediately? Three. Yeah, the nitrate rule. Because we know that Big Daddy says that if nitrate is in a compound, it's automatically soluble. All right, because Big Daddy looks at nitrates. So if you drop silver nitrate in water, it dissolves. That's all it's telling us. Let's do another one. Sodium chloride. What rule do you see activate here? So rule 1, yeah, there's another Big Daddy activating because the alkali metal's automatically aqueous. But what other rule is also present here? Rule 2. Yeah, because Rule 2 says that the halogens are usually soluble. There are exceptions, but sodium's not one of them. But it wouldn't matter if it was because sodium's a Big Daddy rule, right? But anyway, automatically soluble. Yeah. Do one more. Lead 2 bromide. All right, lead 2 bromide looks like this. Let's draw a card and get a guess. Let's head over to cluster 5. It's a very small cluster. Seat 5. Hey, Aspen, it's going to be you. What do you think? The guess is solid. Do you like that guess? It's a good guess. You can pass the bird. Anybody want to tell me which rule tells us it's solid? Yeah, it's rule number 2 again. So look, in case you don't see, rule number 2 says that bromides are usually aqueous. So it's supposed to be AQ, but one of the exceptions is lead 2. So if it's bonded to one of those exceptions, it gets the opposite label. If you drop lead 2 bromide in water, it just sinks to the bottom. All right. More importantly for us, if you produce lead 2 bromide in a reaction, it precipitates into a solid you can see. The screen mentions what's called the common ion effect. They really like to splash this new thing that you haven't heard of into justification parts of FRQs. So it's important that you listen to what I'm about to say. We are very used to water being the universal solvent. If we make a solution here, we're making it in water. But there are lots and lots of lab situations where your solvent is a solution that's already made, meaning that I'm going to dissolve my sodium chloride in a solution of silver nitrate, right? So I'm going to be dumping the solid version of this into the liquid version of that, and the reaction happens, and you're just making dynamic solutions at that point. What the common ion effect states is that if you are dropping a compound, a solid compound, into a solution that contains ions in that compound, it's automatically less soluble. So it gives you the example there, right? If you add zinc hydroxide solid into a solution of zinc chloride, the common ion effect says that it's not going to dissolve as much as it would in water. Because there's an ion being shared. And again, they really like this to be on your brain for justification purposes. Does that make sense? All right. So let's apply it to a big bad skill. Your ability to write complete ionic and net ionic equations. is super essential. They've never written an AP exam without it. Like one of the things that you'll hear me say a lot is I'll teach something, I'll be like, but I haven't seen it on the test in like 3 years. That happens a lot. We cover so much stuff, and the test, I mean, the test is still really long, but every year there's a bunch of stuff that I teach that they just didn't put on the test that year. And you'll hear me highlight, though, things that are on every single exam. And you'll be doing this more than once on the exam, but on the FRQ for sure. There will be a reaction somewhere that you have to break down into a complete ionic and a net ionic. So you want to be good at this stuff. So if you remember, the complete ionic is the really long version where we break down everything that breaks down, while the net ionic is the shorter version of that, which only looks at items that are changing because we remove spectator ions. I'll remind you what all of that means. Let's give it a go. All right, on the screen it says potassium chloride is combined with lead 2 nitrate. So we've got a bunch of stuff that we have to do here. So follow along with me. You've got your periodic table and your polyatomic handy. I just like you to have that so you can prove charges. As I'm doing the nomenclature quickly, I don't like it when you just trust me. I mess up sometimes, so verify if you have the ability to. Here we go. Potassium chloride, +1 -1, no crisscross, is combined with lead 2 nitrate. Lead 2 nitrate looks like this. The way that I know that is that it's lead 2, so it's the charge of 2. Nitrate, you can verify is 1, and if you cross the 2 and the 1, you get the formula that I wrote. Now, here's where we do have to predict products. I mentioned that you don't have to do synthesis, decomp, and single replacement in AP Chem, but you do have to do double replacement. So this is where we just swap the first part of each compound. All right, so every single compound has 2 different sides. In order to get the products, all we do, just like last year, is you identify, don't write this, I wouldn't write this for you, but you identify the first part of each compound, and on the other side, they're just going to switch places. So I'm writing this kind of dramatically. I want you to get really good and quick at it. But that means that the chlorine isn't going to move, and that means that the nitrate isn't going to move. All right, so we have Cl and we have nitrate. Those are staying exactly where they are. But we are swapping the Pb and the K. So now the lead 2 will be right there, and the potassium will be right there. Yeah? That's all of the prediction of products that we do in here. There's some combustion stuff that we do second semester, but we're far away from that. Now, you do have to check your nomenclature again, though. All right? To make sure these are written correctly. It's lead 2, and chlorine is -1, so there is a crisscross that's going to happen there. So we are always being very careful with our nomenclature. Potassium is +1 and nitrate's -1. You can verify, or you can tell me you don't know where it is and I'll come point it out to you. But there's no crisscross there. All right, what should we do next? Our point, remember, we're trying to get to a net ionic. We're going to break down everything that breaks down. What should we do next? Balance, yes, balance. An unbalanced equation is always wrong. So let's make sure we're balanced. Hey, look, 2 nitrates. So we need there to be 2 nitrates. Hey, look, 2 potassiums. So we want there to be 2 potassiums, 2 chlorines, 1 lead, 1 lead. Make sure you balance. Now we can check solubilities. The only way I can write a complete and net ionic is if I know what breaks apart, dissolves, dissociates, and what doesn't. So here we go. Watch me think through it. Based on rule 1 and rule 2, I know that this dude is aqueous. Big Daddy says that alkali metals are aqueous. What about lead 2 nitrate, aqueous or solid? Aqueous, because of rule 3. Rule 3 says nitrates, always aqueous. We love Big Daddy, or he will hit us. No, you don't want to see him angry. That dude drinks. Okay. What about lead 2 chloride? That dude is solid, right? Look at rule number 2. Rule number 2 states that chlorine is usually soluble, but not when it's bonded to lead. There's a precipitate, yeah? And then what about that final product? Aqueous, because of rule 1 and rule 3. You'll get good at, and by the way, you don't have to refer to the rules by their numbers. I'm doing that so you can look. All right. At no point in time is there going to be a multiple choice question that's like, which of the solubility rules? That doesn't exist. Just pointing out where it lives. How are we doing? Okay. Now we can write a complete ionic. A complete ionic is where you simply break apart everything that's aqueous. All right. But when you do, you account for its charge because it's going to be an ion now, and you account for how many there are. So we've got to be careful with those coefficients. Watch how it works. This dude is soluble, so he is going to break apart into 2 potassium ions and 2 chlorides. You see how I let the coefficient still guide while showing the charges? There's a fly hanging out with me. That go with it, all right? Now we go to the next product. Hey, look, he's aqueous. He is going to dissociate into 1 lead. What's lead's charge, though? Yeah, it's +2. Just make sure you show the charge and how many there are. How many nitrates are there? There are 2 nitrates. So you might remember that this is the moment where subscripts can suddenly represent themselves as coefficients, because it's all about numbers. When this breaks apart, for every one of those, there are 2 of those. Hey, check it out. Our first product does not dissociate, so leave them together. But the other product does. Aqueous, so it's going to go and dissociate into 2 potassiums and 2 nitrates. Now, if you're a really good scientist, you will bring down these states of matter. They don't take the points away if you don't bring it down, but I mean, I'm gonna model good chemistry, but I just showed those states of matter along with everything. All right, so this is the complete reaction. This is the complete ionic reaction, and now we'll write the net ionic. The net ionic is the same thing, but without the spectator ions. By definition, a spectator ion is an ion that doesn't change during the reaction. It's the same as a reactant as it is as a product. So what you're looking for is copies. Here's the spectators that I see. Now, I'm going to draw little lines. I don't suggest that you get dramatic about it in your notes, or it makes your notes look ugly, because it could ask for a complete ionic. If you run into a question that says, what's the complete ionic? That's the answer. You don't got to start crossing stuff out. Know where to stop. But if we're going to go to the net ionic, do you see how the 2 potassium ions copy themselves? There is a spectator. Do you see how the 2 nitrate ions, they copy themselves on the 2 sides of the yield? Those are spectator ions. Leaving us with a net ionic.
Good morning, teachers. Happy Monday. This is a friendly reminder that you must take a second period attendance. If you want to hold a student program, please get to the attendance office at this time. Thank you. Have a great day.
Chemical reaction, complete ionic reaction if you don't count the crossouts, net ionic reaction because I remove the spectators. Let's do another one, but we'll draw some cards. I'll do the initial translating because I don't want us to lose time on a skill from last unit. So here we go. Silver is Ag. Nitrate is NO3. That is +1, that is -1, so there's no crisscross. Reacts with magnesium bromide. Magnesium is Mg. Bromide is a bonded bromine. That is +2 -1. So if you've got a 2 and a 1, there will be a crisscross. All right, let's draw a card. Let's go over to cluster 2, seat 5. How'd that feel? Hey, 2-5, can you tell me what one of the products are? Just one of the compounds, little form. I don't care which one. So remember what we do. We're going to do that swap where we just switch the first part of each one. So I'll rephrase my question. If magnesium comes to right there, what would one of the products be? Perfect. MgNO3. All right, I'll fix the nomenclature in a moment. The other product would be silver moving over to there, making it silver bromide. Yeah, I know. I'm going to fix the nomenclature. I know. I'm on my way there. Make sure you check your nomenclature, though. Magnesium +2, nitrate -1, silver +1, bromine -1, and crisscross. Yeah? What's next? Balance. Don't forget to balance. There are 2 NO3s, so I need there to be 2 NO3s. There are 2 AGs, so I need there to be 2 AGs. And I think that fixes it. All right. We want to get to a net ionic, but first I need the solubilities. All right, let's go pick on some people. Let's go over to cluster 5, seat 4. Hey, Aspen. Solubility of that reactant, what do you think?
I think it's soluble.
It is soluble, very good, because of rule number 3. What about that one? Do you want to keep going? You can get rid of me if you want.
Yeah. Oh wait.
Rule number 2.
Soluble.
Yep, also soluble. All right. This is rule number 3, makes him soluble. Rule number 2 makes him soluble. Is everybody cool? Stop me if you don't see it. I will come and point it out to you. All right. Let's go somewhere else. Let's go over to cluster 3, seat 3. Hey, 3-3. Kaylin, what about this one? Focus on the nitrate, the NO3. Look at rule number 3 pertaining to nitrates. Totally soluble. Whoa, I'm losing my mind. What about the other product, anybody? Solid, yeah. The other one is a precipitate because of rule number 2. Rule number 2 makes him solid. Do you see it? Very good, very good. All right, let's go complete ionic. If it breaks apart, break it apart. AQ, it does dissociate, so here we go. There are 2 silvers, so there's going to be 2 silver ions, all right? When it dissociates, floats around as an ion. Love each other, please. And 2 nitrates. The other reactant, also aqueous, also dissociates into magnesium ion and 2 bromides. Careful with those subscripts. I know it's a little different, but you will get used to it. Of course, remember, ions don't follow diatomics. We covered that Friday, which is why we're not dropping little 2s. A little 2 for bromine. Hey, look, my first product does dissociate. So there is 1 magnesium there and 2 nitrates. The last product is solid, does not dissociate. In blue is the complete ionic. To find a net ionic, I need spectators. Let's go talk to somebody. Let's go over to cluster 2. Could it possibly happen again? Seat 3. Aspen, it's you. Hey, Aspen, can you just find me a spectator? Oh, did you get Aspen already? Oh. Why are you hogging the bird? Just kidding. Hey, Aspen, can you pick out a it was supposed to call on you. Can you just find a spectator for me? All right, yep, 2 NO3s, and now you can pass the bird. Yep, there's 2 nitrates. Whoa. There's 2 nitrates and 2 nitrates. Again, you just need anything that is a duplicate on both sides. Hey, anybody, what's another one? Yeah, the magnesium ion. Magnesium ion and magnesium ion. And now we're ready for a net ionic. That looks like this. Any questions? Well, we wish it could just be like that, right? Unfortunately, there is a second type of reaction that we have to worry about. Those were what's called double replacement, where we're just using salt. Neutralization is the same thing. It's still double replacement, essentially, where it's going to do that exact same ion swap. But the rules are a little more mean here. If you're dealing with acids and bases, the AQs and the S's are a little bit different. Or rather, whether or not they break apart in solution. What's going to happen for acids and bases is weak versus strong. Only strong samples completely dissociate. We covered that on Friday, which means if you identify a weak sample, but it's an acid base, you're going to keep it together even though it's labeled aqueous. Let's take a look at what I just said. All right, sodium hydroxide is mixed with phosphoric acid. That sounds like fun. Here we go. Sodium is Na. hydroxide is OH. +1, -1, no cross. Phosphoric acid. Now your acidic nomenclature suddenly rings true here, right? Because remember, you don't get that on the AP exam. You have to know your acid rules. So a lot going on here. All right, but phosphoric acid looks like this. H3PO4. Because it was 8, it was phosphate, and 8 became ick. All right, all of those rules to get me to the phosphate, but it has a 3 that it crosses over. Now, one of the things on the previous slide reminded you from last year, because we did this last year, that in neutralization, an acid reacting with a base, it always makes salt and water. We'll prove it with the ion swap. Like, it's nice to know that fact. But if you switch the H and the Na, it's going to be HOH, which is H2O. And then salt, which is any ionic compound is salt. In this case, sodium phosphate. So switch them, and you're going to get HOH, but I'm going to write it like a grown-up. And the sodium is going to marry phosphate. But this is +1 -3, so there will be a cross. Everybody all right with that? Balance. Hey, see the 3 sodiums? Let's make there be 3 sodiums. This one's a little more fun to see. You see the 6 H's? There's 6 H's. There's 3 there and 3 there. So I need there to be 6 H's. Now there's 6, and you'll see that you are actually balanced. Now, if you follow solubility rules, you would label these as aqueous, but we don't need to do that. Acids and bases are always electrolytic. We went over that on Friday. What we need to do for the purpose of net ionic when using acids and bases is strong versus weak. So let's see who learned something last week. Sodium hydroxide, strong or weak? It's strong. The reason I know it's strong is it's an group 1 metal hydroxide. H3PO4, weak or strong? It's weak. Why? Because the H to O ratio. Yeah, not ivory and clay. Ivory and clay is only for binaries. This is non-binary because there's multiple elements. But there are not at least 2 more O's than H's, making it weak. That's really important. Now, the other side, though, is going to follow normal stuff because the salt is the solubility rules at the beginning of this lecture. And water's actually kind of fun. What state of matter is water? It's liquid, yeah. That's a cursive L. I don't mean to blow your mind, but if I don't make it cursive, it looks like a 1. As we had a conversation last period, or on Friday, about 1s. What about sodium phosphate over here? What's the solubility of that salt? Yeah, he's aqueous because of rule number 1. Right, rule number 1, alkali metals. So these dudes, as I said, are aqueous though. All right, the solid and weak circles I put up there, that's not official chemistry. That's what you're thinking in your brain. But it's, yes. Because all acids and bases are electrolytic to some degree, regardless. So remember that those rules, everyone listen to this. Those rules at the beginning of today only govern salts, which is this over here. Acids and bases are in their own world. All right, so you don't actually apply the opening rules to acids and bases. They have their own rules. They're always aqueous, strong and weak matter. Complete ionic. Here we go. Acid, strong, does dissociate. This guy's going to break apart into 3 sodium ions and 3 hydroxide ions. Look here, it's a big change. Acid, weak, doesn't dissociate, even though it's got the aqueous label, and I know this messes you up. The strength of acids and bases matter more than their state of matter. Can liquids dissociate? Maybe you don't know. Now you do. No, they can't. The liquid state never dissociates. So you see that liquid water? Stays water. What about aqueous salts? They do dissociate, right? We just spent 20 minutes doing that. So he's going to break apart into 3 sodium ions and a phosphate ion. Who's got questions? Yep. Nope. Not at all. All right, that's complete ionic. Let's find net ionic by eliminating spectator ions. Let's see if we can find them. See the 3 sodiums and the 3 sodiums? That looks very spectatory to me. Do you see any others? That's it. Those are the only spectator ions. So now let's bring it down. Net ionic. Yeah? You can do one of these without me? For sure, for sure. Where you at, bro? There she is. I'll do the translating for you because I don't want you to get stuck on that. But let's see how much of this you can do. It says hydrochloric acid reacts with potassium hydroxide. I want the net ionic equation. Hydrochloric acid is HCl, as I'm sure you know. Potassium hydroxide is KOH. +1, -1, so there's no crisscross on either one of those compounds. Everything has a charge of 1 in some form. You got this. Say it again, I'm sorry. But no, they're on their own. So is HCl weaker? I agree. Oh, okay. Well, there you go. Yeah. Okay. So it's I forgot that lecture. Yeah. So it's binary where it's H one element. It's strong only if it's iodine, bromine, or correct. For these dudes, for the hydroxides, it's strong if the thing connected to it is an includes one. Yeah, it's here, or if it's calcium strong. Yep. I'm going to start working silently up here. You're welcome to glance if you want to check what you're doing. I labeled both reactants as strong because binary I bring clay, strong. Group 1 metal hydroxide, strong. Therefore, they're both going to dissociate. Ion swap gave me salt and water. That always happens when an acid reacts with a base. For the balancing purposes, I gave you a very easy one because it's a 1 to 1 to 1 to 1 mole ratio. You're welcome. And then I find my spectators. Now, it's my opinion that it's beneficial for you to know that this always connects to that green answer. That this sentence right here always connects to the net ionic that you just got. H plus plus OH minus equals water. Very good common knowledge. So if you know right up front that it's a strong acid, strong base, that is always the net ionic equation. It can't be anything else. I don't get to give you a lot of absolutes in here. That's an absolute. Strong neutralization has a net ionic equation of hydrogen ion, hydroxide ion, forming water. Now, just like Friday, I have to end by being mean to you. So, did any of y'all go and watch that 4-minute video that I told you to watch? All right, it got some hits over the weekend, so kudos for being a good student. That was for Friday's lecture. So this one's 13 minutes long. I'm sorry. I'm a mean teacher, right? But on Wednesday's lecture, I'm not going to do this to you. So I promise it's not a super regular thing. But on Canvas, where the videos are, there is a 13-minute clip of me solving this, which, again, it's just marrying concepts together. Very awesome for you to watch it. You'll be smarter. Good job today.